Absorption affects all electromagnetic waves that pass through our atmosphere, but it affects some frequencies more than others. Fortunately for us, nearly all high-frequency waves are blocked by the upper atmosphere, so we are protected from X-rays or gamma rays coming from space. But if we want to have telescopes that look at those particular frequencies, they have to be stationed in orbit above the atmosphere. And astronauts in the International Space Station need special shielding around their living quarters because they're not protected from these rays as we are at ground level. Even people who are flying in planes at high altitudes are getting a little bit more exposed to rays from space than we are down on the ground. In fact, only 2 bands from the whole spectrum make it all the way down to Earth's surface. And we call them windows in the electromagnetic spectrum. So we have the visible window, which means that we can see the sun and stars and things in space. And there's also a radio window that means that we can use radio telescopes to detect radio waves coming down from space. When we look at a glass of water, we imagine that it looks transparent and so it must be letting all colours of light pass through equally. But if you look at light travelling a long distance through water, you will find that in fact the red part of the spectrum is being absorbed a lot more than the blue and green. And so since the red is attenuated more than other colours, if you go diving underwater, you will find that things look progressively bluer as you look further away, as more and more of the red is being subtracted from the visible spectrum. Optical fibres are being used more and more in communications. We know that they use laser light, and we often assume that they're in fact using visible light because we see pictures of them with light shining through. But in fact, the lasers used in optical fibre communications are infrared radiation, and they generally come from an erbium laser, and the wavelength is about 1500 nanometers, well beyond the 700 or so nanometer limit of the visible spectrum. The reason is that fibres sometimes need to run for thousands of kilometers, and in long-distance communication, you need to minimize the attenuation of your signal from absorption. So fibres are made from very high purity glass, and that glass has a minimum of absorption, as you can see in the graph there, at about 1500 nanometers. And so that is the wavelength generally used for long-distance communications.